Imagine a world where everything is the opposite. Up is down, left is right, and matter has an evil twin antimatter. It sounds like something straight out of science fiction, but antimatter is very real. It's the bizarre counterpart to the ordinary matter that makes up everything we see and touch. But here's the catch. Antimatter is incredibly rare in our universe. For every particle of matter there seems to be a tiny, almost non-existent amount of antimatter. Why this is the case remains one of the biggest mysteries in modern physics. So what exactly is antimatter? Simply put, it's a substance composed of antiparticles. These antiparticles are like mirror images of the particles we know and love, but with opposite charges. Think of it like this. If an electron is a tiny, negatively charged particle, its antimatter counterpart, the positron, is a tiny, positively charged particle. It's like looking into a cosmic mirror and seeing a reversed version of our universe. Let's meet some of these fascinating antiparticles. We've already been introduced to the positron, the antimatter twin of the electron, but there's more. The antiproton is the antimatter version of the proton, a positively charged particle found in the nucleus of every atom. The antiproton, as you might guess, is negatively charged, and then there's the antineutron, the neutral counterpart to the neutron. These antiparticles aren't just theoretical constructs. Scientists have been able to create and study them in laboratories, albeit in extremely small quantities and for very brief periods. The reason for this is simple. Antimatter doesn't last long in our matter-dominated universe. As soon as an antiparticle comes into contact with its corresponding particle, they annihilate each other in a burst of pure energy. Annihilation. It sounds dramatic, doesn't it? And it is. When matter and antimatter collide, they don't just disappear. Instead, they transform into pure energy, following Einstein's famous equation, EmC2. This equation tells us that mass, m, and energy, E, are interchangeable. And a tiny amount of mass can release an enormous amount of energy. This is what makes antimatter so potentially powerful. Imagine a future where antimatter could fuel our spaceships or power our cities. A tiny amount of antimatter could theoretically produce a tremendous amount of energy, far exceeding anything we can achieve with current technologies. But there's a catch, isn't there always? Creating and storing antimatter is incredibly difficult and expensive. Here's a cosmic puzzle that keeps physicists up at night. If the Big Bang created equal amounts of matter and antimatter as current theories suggest, where did all the antimatter go? Why is our universe dominated by matter? This is known as the baryon asymmetry problem, and it's one of the most fundamental unanswered questions in cosmology. One possibility is that there's a subtle difference in the behavior of matter and antimatter, a difference that we haven't yet detected. Another possibility is that there are vast regions of antimatter somewhere out there in the universe, hidden from our view. But so far, we haven't found any evidence to support this idea. The mystery of the missing antimatter remains one of the most intriguing puzzles in our quest to understand the universe. Section 5. Creating antimatter, a tiny explosion of energy. If antimatter is so rare, how do we even know it exists? Well, we can create it. Scientists use powerful machines called particle accelerators to smash atoms together at incredibly high speeds. These collisions are like miniature Big Bangs, releasing enough energy to create tiny amounts of antimatter. The most famous of these machines is the Large Hadron Collider, or LHC, at CERN in Switzerland. The LHC is a colossal underground ring that accelerates protons to nearly the speed of light and then smashes them head-on. These collisions produce a shower of particles, including, you guessed it, antimatter. However, the amounts of antimatter created in these experiments are incredibly small, far too little for any practical applications. We're talking about billionths of a gram or less. Section 6. Antimatter's potential, from medicine to the stars. Despite the challenges, the potential applications of antimatter are incredibly exciting. In medicine, for example, positron emission tomography, or PET scans, use positrons to create detailed images of the inside of the human body. Antimatter could also revolutionize energy production. As we've seen, the annihilation of matter and antimatter releases enormous amounts of energy. A tiny amount of antimatter could theoretically power entire cities for days, weeks, or even longer. And then there's space travel. Antimatter could be the ultimate fuel for interstellar voyages, allowing us to reach distant stars and explore the cosmos like never before. Imagine a spacecraft propelled by the annihilation of matter and antimatter, reaching speeds that would make even the Starship Enterprise jealous. Section 7. The Perils of Antimatter Handling the Unthinkable. But before we get carried away with dreams of antimatter-powered spaceships, we need to address the elephant in the room. Handling antimatter is incredibly dangerous. Remember what happens when matter and antimatter meet? Annihilation. Even the tiniest speck of antimatter coming into contact with ordinary matter would result in a catastrophic release of energy. Storing antimatter is like trying to hold lightning in a bottle. Scientists have developed ingenious ways to trap antimatter using magnetic fields, preventing it from touching the walls of its container. But these traps are incredibly complex and delicate, and the slightest malfunction could have disastrous consequences. Section 8. The Baryon Asymmetry, a Cosmic Puzzle. Let's return to that cosmic mystery we touched upon earlier, the Baryon asymmetry problem. Why is there so much more matter than antimatter in the universe? It's one of the biggest unanswered questions in physics, and it has profound implications for our understanding of the cosmos. Some theories suggest that there might be a subtle difference in the way matter and antimatter behave, a difference that gave matter a slight edge in the early universe. Others propose that there are vast regions of antimatter somewhere out there in the cosmos, hidden from our view. Solving the baryon asymmetry problem is crucial for understanding the origin, evolution, and ultimately the fate of our universe. Section 9. Antimatter's Future, a Universe of Possibilities? Antimatter may seem like the stuff of science fiction, but it's a real phenomenon with the potential to revolutionize our world. While the challenges of producing, storing, and utilizing antimatter are immense, the rewards could be equally enormous. Imagine a future where antimatter fuels our cities, propels our spacecraft to the stars, and helps us unlock the deepest secrets of the universe. The possibilities are as vast and mysterious as the antimatter itself. As we continue to explore the universe and unravel its mysteries, antimatter will undoubtedly continue to fascinate and inspire us. Who knows what incredible discoveries await us in this strange and wonderful mirror world of antimatter?